Thanks, Mark, for the introduction and for inviting me to come out here. It's a great pleasure to be here. So my talk today will be on contact and sort of overall in my lab. We're working on getting robots to work in the real world, and that's thinking about challenging outdoor terrain, deserts, forests, that kind of thing, as well as sort of messy human environments. We do less in the sort of warehouse, factory kind of space. And some of the applications we're looking at include things like planetary exploration stuff. We have a big project here in environmental monitoring. So sending a robot out specifically to look for contaminants in soils, like asbestos or mercury or lead or that kind of thing, with mobile robots that are digging and playing around in the dirt. And all right, so if we want robots to get out into the real world, what's the sort of challenge? Why is this a hard problem? And so this was the video that was playing at the beginning. This is sort of a blooper reel of taking some legged robots out to the park behind campus. And in each of these clips, what I want you to take away is that the problem was that there was unexpected contact with the world. Either it tried to put its foot down and there was nothing there, or here it's touching these vines that it doesn't know anything about. You know, maybe it's got a camera or a laser scanner, and you can see the top of this plant, but it's not going to see the ground that it's actually stepping on, and it's not going to be able to pick out the vine that it's hooked on. So all of these, either it's bumping into something it doesn't know about, or it's trying to touch something and missing. And this is a challenge not just for robots, but also humans. So here's a YouTube video from a subway stair in New York City that over time has settled so that one step is slightly taller than all of the other steps. And everyone that goes by, you know, they're taking their legs over the stair. They think they can clear the stair, and they can't quite. And that one little tiny bump on your foot causes you to trip, right? So this challenge with, you know, contact with the world being different than you expect is a big problem. You know, it also comes up in manipulation. So here's another blooper reel of trying to pick up little objects. And again, all of these, I think, come down to either the friction's a little different than we thought, or we bump into it early, or it just whiffs and slightly misses the contact that it's trying to make. So most of the projects in my lab kind of fall into these sort of two key challenges. The first being contact, and in particular, the discontinuous nature of contact. So when your foot is on the ground, you have large contact forces. And when your foot is a millimeter above the ground, you get no contact force. And that discontinuity causes a lot of problems. All of our sort of traditional state estimation, control, learning, all of these things at some level assume continuous, if not smooth or something stronger in our dynamics. And then the second key challenge is uncertainty. So maybe we can have a good model of our robot, but we're not going to have a good model of how squishy that pile of leaves is, or what's the friction coefficient on this rock. And so rather than trying to do better and better perception and get a perfect model of the world and learn a perfect dynamics model, I don't think that's possible for what we're doing. And so we want to instead come up with approaches that don't need a perfect model and can handle this kind of large uncertainty that we're going to have. So then with these kind of key themes of contact and uncertainty and looking towards getting robots out into challenging environments, we kind of work on all areas of robotics. So we do controls, we do design, we do some learning and vision. And today I'm going to mostly talk about stuff more on the controls side. And in particular, I'm going to spend the first half or so, maybe two-thirds, talking about techniques for using what I call hybrid dynamical systems. And it's one way to sort of model contacts, and then with certain assumptions. And then in the last third, I'll talk about examples that break all of those assumptions, and we'll see where that doesn't hold. So when do these sort of hybrid models work well? So the hybrid system, the hybridness, the word hybrid there means that it's a combination of continuous state and discrete state. And for us, that's going to be discrete state is going to be our contact conditions. So touching and not touching, as well as things like stick and slip friction. And for for robots like in these videos, this kind of hybrid model works pretty well. And what I say is if you can take a video of your robot, play it back, maybe play it back slow, but if you can watch the video and say, here's where it's touching, here's where it's not, here's where it's touching, then this kind of hybrid system model is a good approximation. And that covers a lot of what we do in robotics with sort of manipulation and locomotion tasks. It's not everything. So here's a bunch of examples where I think these kinds of hybrid models that I'm going to talk about don't work well. And so things like interacting with fabric, where there's not this kind of discrete contact, no contact, and then sand, where it's this sort of continually flowing media. We're not going to slow down this video and look at the particles of sand and look at, all right, when are they touching, when are they not touching, right? So for all of these examples, the hybrid system models that I'm talking about in the first half maybe aren't a good approximation, and we'll cover some of this stuff near the end. So the first thing I want to talk about is trying to do state estimations, trying to understand what our state is in the world when we have these kind of contacts in a hybrid system framework. And the sort of most basic fundamental state estimation algorithm is Kalman filtering. And so if it's been a minute since you've done Kalman filtering, or even if you're very familiar, just to get us all on the same page, here's a quick rundown. So in Kalman filtering, we're going to have some estimate of our state. That's the blue dot in the middle. And then we'll have some covariance, some uncertainty around that state. And there's two steps in Kalman filtering. The first step, we're going to propagate that forward and predict where we'll be at the next time step. So that involves taking our dynamics and moving our estimate forward in time, as well as our covariance, and seeing how our covariance will grow or shrink over time. And in particular, we usually add some extra noise. So the covariance is typically going to grow over time as we get farther and farther from our initial condition. Then to reduce our uncertainty, to become more certain about where our state is, we'll take some measurement. So there's some sensor. Maybe we can see that little feature in the corner of the slide. And based on our sensor model, we say, all right, that means I'm probably over here, but there's some noise in the sensor, so there's some uncertainty there. And Kalman filtering tells us the best way to combine these two estimates into a new best estimate of our state and covariance based on our prior and our measurement. All right, so that's like a whole lecture's worth of Controls 101 in one slide. So if we want to do this kind of state estimation with a hybrid system, so now we're going to impact the ground. So I'll explain this in the sort of that first step, the prediction step, but it's pretty similar if we do it in the measurement step as well. But let's say somewhere along that time, our foot hits the ground or our hand touches an object. When we updated our mean in this sort of continuous regime, we applied our dynamics, and then our covariance was propagated with the Jacobian of the dynamics. So this is the A matrix in controls. And so when we get to an impact, we have a model of that impact, which I'll call the reset map, but this is your plastic impact, elastic impact. We have some forward prediction of how the velocity will change when we impact an object. And so we can use that to update our mean. And then for the covariance, we might think that we could use the Jacobian of the reset map, so the Jacobian of our impact dynamics, to update that covariance. And this turns out not to work. And to see why, I'm going to show here a very simple hybrid system. So picture on the left is kind of like my leg is in the air, and on the right is my leg is touching the ground. In this case, the dynamics on the left are constant vector field. So everything's just moving down and to the right. And on the right, we have a constant vector field slightly up and to the right. In the middle would be that impact time. And in this case, I'm showing that there's no jump. So the reset map itself is an identity. So there's no change in state at the boundary. So on the left, constant velocity. So that means nothing's growing or shrinking. On the right, constant velocity. Nothing's growing or shrinking. And in the middle, we have an identity function. Nothing's changing at the middle. So nothing changes on the left, nothing changes on the right, nothing changes in the middle. And yet, as our distribution of our sort of uncertain state here goes through this transition, the covariance is changing. It's getting stretched out. And so if we just used the Jacobian of our impact, of our reset map, then we would say that the covariance at the end should match the covariance at the beginning, which is the red circle. And so that doesn't capture this at all. So how can we propagate our sort of covariance through this kind of transition? And the key tool that we need to do this is called the saltation matrix. It basically maps if there's some displacement or variance before an impact, how does that translate to a variance afterwards? And the formula for it, you can ignore the details, but basically the saltation matrix, it starts with that Jacobian of the reset map. So we do need to know the derivatives of what that impact dynamics are. And then there's all this other junk. All right, and what's over here, again, the details aren't important, but it's like the dynamics in our new mode, the dynamics in the old mode, what that boundary looks like, as well as time derivatives of all these things. And I'll be honest, the first time I saw this equation, I said, this is way too messy. There's no way this is important. Right? It's this big, ugly thing. You need a million little terms to compute. How is this useful? But it turns out that you really do need to account for all of this. And what these extra terms are doing is accounting for the fact that if you're a little bit ahead or a little bit behind of the nominal trajectory, you're going to spend more time in one mode versus the other mode. And so this is accounting for that difference in impact timing that then leads to that sort of skewing we saw before. And so after just realizing that this is actually very important, I mean, it's been known for, I think the earliest place that we've seen this show up was somewhere in the 50s. So it's not that this matrix is new, but we're sort of applying it in new ways and bringing it to the robotics community. So to help with that, we wrote this tutorial, sort of survey tutorial thing in Proceedings of the IEEE that just came out. So if you're come out of this and say, I guess I need to think about this, hopefully we've written like a nice, gentle introduction to it so that you're not just stuck staring at this ugly equation. All right, so with this saltation matrix thing, now when if we want to propagate our covariance, so if this is our initial covariance, we can map it over here on the right. In black is the actual covariance of this set of particles, and then in yellow dash is the saltation matrix prediction, which is exact in this kind of linear case. So now we can update our covariance estimates through these kinds of transitions. And so we can put this back into our Kalman filter. So now our continuous predictions, when we're not impacting anything, nothing has changed. This is just like a regular Kalman filter or extended Kalman filter. And then when we have an impact event, we apply our reset dynamics, so our impact law, to the mean, but then we use this covariance, this saltation matrix to update the covariance. And that ends up being the key to getting state estimation for these kinds of hybrid systems. So what does this look like? So if we try and do state estimation and track our state through this kind of two-phase system, I call this the cheese grater system, sort of sliding through that middle line in the middle. What we see here, this is the error in our estimate. If we just use that Jacobian of the reset map, we get much higher error. And then if we use this saltation matrix, we get pretty good tracking on that. And a couple things to note before the impact, so the impact happens, or the transition happens somewhere in the middle here. Before that, it's exactly the same, right? Because it's just a Kalman filter other than at the time of impact. And then afterwards, it's better. There's still a little bit, we're sort of not quite as good as the sort of best possible estimate right around the impact. And that's because this is still a local linear approximation. So we're still saying that the mean either has transitioned or not transitioned. And we sort of move all of the probability across at once. And so that's sort of one limitation here that we might want to improve eventually. But once we've sort of gotten all the way through the transition, we have the correct estimate for the covariance. We can apply this to more complicated systems. So here, this is a asymmetric slip hopper, so like a legged hopping robot with 6 states and nonlinear. And this one actually has a jump at the impact. Right, the last one there was no actual impact law. And here, if we compare again, blue is this saltation matrix thing, and red is if we just take the Jacobian of the reset map. It actually looks pretty similar in every dimension except one. So here in Y, so in the vertical direction, we're getting much better state estimate tracking. And that's because the saltation matrix is actually, it's a rank 1 update. it's just correcting in the direction of the guard, right? Because it's that time to impact difference. And so only in the direction of the normal vector of your guard, we're going to have a much better estimate because we're counting for variances in that direction. So we can extend this now to, we've extended it to when we're not certain about exactly where that transition happens. So here, instead of just a solid line, there's this gray set of lines, and each particle has a randomly sampled transition point. So now if we aren't sure exactly how high the ground is or what the surface normal is, we can kind of account for that uncertainty as well. We're working now on maintaining belief in multiple different modes. But this works really well in terms of just state estimation. And then this idea of how do we propagate covariance through this transition, we can do the dual problem. So the dual to state estimation would be control. And so if we want to do trajectory optimization or model predictive control, we can use the same idea in an ILQR-based trajectory optimization. So in ILQR, you have to sort of propagate your gradients backwards, propagate your value function. And just like with the covariance, when you go through this transition, you need to use the saltation matrix to propagate that appropriately. And so with that, this is comparing sort of a standard model predictive controller with this hybrid ILQR model predictive controller. And we hit the robot, and then it's able to come up with a new set of footfall conditions. So one of the nice things that comes out of this is that it's able to change those contact timings and change those contact sequences to come up with a better way to catch itself after a disturbance. We've run this on the actual robot as well. Here, to get a consistent disturbance, we just turn off the motors for 150 milliseconds and let it fall, and then try and catch itself. And again, this sort of standard model predictive controller gets totally lost because it thinks all the legs are off of the ground. But with this ILQR model predictive controller, it can say, oh, I need to put my feet back down and catch myself from there. So this saltation matrix helps with both sort of state estimation and control techniques. The next thing I want to talk about is stability and sort of analyzing behavior. And maybe we're coming up with a controller or maybe we're not. And for this, I'm going to go through 3 examples of heuristic controllers, heuristic properties that we've seen in the past. And I'll show how they're all related and how, in fact, all of them use the same saltation matrix to capture them. So we're going to go through 3 examples. The first example is a paddle juggler. So picture you've got a tennis racket and a tennis ball, and you're bouncing the tennis ball, right? And you're trying to balance it to maybe a consistent height, all right? Now, the dynamics of this, so your control input is just moving the paddle. And so you're really only affecting the ball at the moment of impact, all right? And the dynamics for that impact say that it depends on the velocity of the ball and the velocity of the paddle. So it matters the position and the velocity that we impact the ball with. It turns out to stabilize this, if you want to bounce it at a stable height and with stable timing, you need to impact it with the nominal velocity, but with a negative acceleration. You need to be decelerating as you come up. And the intuition behind this is if the ball has too much energy, it'll go higher, so it'll take longer. And so when it comes back down, you want to be going slower so that you don't impart more energy. You want to take some energy out. If it has not enough energy, it'll impact early, so you want to be going faster. All right, so you want to be decelerating as you impact the ball. But what's interesting is that the dynamics don't have the acceleration term in them at all. So where does this acceleration property come from? So to sort of see this acceleration, this is a little confusing, so let me talk you through it. Here we have 3 paddles, red, yellow, green. They all hit the nominal ball, so the sort of nominal trajectory is in black. They all hit it at the same position and the same velocity. But they have different acceleration. So one is x, the green one is decelerating, the red one is accelerating, and the yellow one is going at a constant velocity. But again, they're all hitting at the nominal time, same position, same velocity. So they all hit the black ball, and the black ball will do the same thing for all of them. So the green paddle hits the green balls, the red one hits the red balls, and we see that this cloud of if we have a little bit of noise in our initial condition, all of the red, green, and yellow sort of started out similarly. Here, those green balls slowly get closer and closer and closer to the nominal trajectory, while the red ones kind of explode, and the yellow ones are somewhere in between. They kind of stay spread out, but they're not getting bigger or smaller uncertainty. All right, so this result that for paddle juggling you need to be decelerating when you impact has been known for a while, actually. So here's a paper from Shaw and Atkinson from 1993 where they show this. And at the top you can see it's accelerating upwards, and the very small initial uncertainty grows to larger and larger. At the bottom we're decelerating, and it's converging to, even with a pretty large sort of initial uncertainty, converges to a single trajectory. All right, so that's example one, is paddle juggling. Yeah, yeah.
Actual value matters, or as long as it's negative, as long as it decelerates, it will have this stabilizing property.
Yeah, there's sort of there's a range of values where it's actually, I think, equally stabilizing, and it matters more in terms of like how far away from the nominal. Because if you're decelerating very quickly, all of a sudden you'll be like going the wrong direction, and so if you're really far from the nominal, then that'll start to come in. Yeah. All right, so that was example one. Example two, swing leg retraction. So if you've ever done anything with legged locomotion or human locomotion, you may be familiar with this. So when you walk, you swing your leg forward, and then you don't want to scuff your foot, right? So the first thing you do is you slow the foot down to try and get it to be roughly the same speed as the ground. And you would think that the optimal would be what people call ground speed matching, right? That we would want no relative velocity because we don't have any sort of tangential impulse. That's not quite what we do. We swing our leg forward, and then it starts to come back just a little bit. And so that's what this is sort of showing here in the stripes. There's this velocity backwards. Afterwards, as you're walking away, you can try and think about if you're actually doing this. If you get a high-speed video, you can watch, and you'll see you really do actually swing your leg back ever so slightly. And the reason is that it improves your stability. So, I mean, this is sort of an eye chart, but the number of stable points increases as the speed of this retraction increases. So if we swing our leg backwards, we get sort of stable locomotion. There's a little bit of a tangent. Before I explain the robot, let's just watch this walking robot. As it swings its leg forward, the forward motion stops, and it's just starting to come back when the leg hits the ground. All right, so here's one example of this. I bring this up, so this is a very simple biped design. We call this Mugatu, but I think this is the simplest walking robot we could have. So this is one motor and two rigid bodies, a left leg and a right leg, and the arms are bolted to the opposite leg. But we're still able to get stable walking. It can start, stop, turn left, turn right, through careful design of the passive dynamics and timing of the control on the one motor. So this guy was pretty cool. This was at Humanoids last year. And I'll be honest, I didn't know that the Humanoids people would think that this is a humanoid enough for them. But we got it in. It's got two legs, but I don't know if it's humanoid for them. But so this was about, I'm going to say 13 centimeters, maybe 15, I forget. About yay big leg length. So it's also pretty small. As a sneak peek here, here's our 2.5 centimeter leg version. Same idea, one motor, two rigid bodies. So this is submitted to ICRA, so hopefully you'll see more of this next summer. All right, sorry, we got on this little tangent with these cute little walking robots. We were talking about swing leg retraction, all right? So that was our second example. Our third example is going to be the Raybert heuristic. So if you have like a hopping robot and you want to control the forward speed, you can control that by changing the angle at which you impact the ground. So if this is sort of your nominal impact, if you come in at a shallower angle, then your leg is going to kind of slow you down. If you come in at a steeper angle, then you're going to kind of fall over your stance leg, and you'll accelerate forward. So again, there's some nominal angle where your forward acceleration is 0. Less than that, you're decelerating, and less than that. So they're measuring this way. You're accelerating, and then if you're shallower, then you're decelerating. And Mark Rabert, he's a genius. He just kind of looked at his robots and figured this out. So this is from a 1984 paper, possibly even before then. So here's a video of his leg lab at Carnegie Mellon at the time, I'll point out. And so that's how these kind of early hopping robots were able to walk stably. And you could sit there with a joystick and say, go faster or go slower. And it's using this leg angle control to change that speed. All right, so these examples 2 and example 3, if you take your swing leg retraction, as well as this Rabert heuristic, you get stable hopping. So here on the left, if we just have a nominal touchdown angle, and here at the beginning of the video, it's kind of hard to see, but there's like 10 slightly ghosted. You almost can't even tell that they're different ones initially. And after it doesn't take long. It's like 2 or 3 steps. They kind of start flying off all over the place. It's actually pretty unstable. But if we have this Rabert heuristic for a forward speed and a swing leg retraction on the timing, we get stable hopping motion. So we had 3 examples. It was the paddle juggler, the Rabert heuristic, and the swing leg retraction. And all of these kind of had a character of we were changing what we were doing around the impact time, and somehow that affected the stability of the whole system. And it turns out that this saltation matrix pops up again. So the way we can describe these systems, if we think about if there was some uncertainty at the beginning, if we go through the whole cycle and come back around, the way that maps onto some error at the end or some uncertainty at the end is called the monodrome matrix. And the way that's built for a hybrid system is this saltation matrix term shows up anytime you have an impact, and then this A matrix for any time you have sort of continuous phase. And you have this sort of intersplicing of your continuous dynamics, your saltation matrix, continuous dynamics, saltation matrix. If we changed something about our impact, like we changed that acceleration, that parameter doesn't show up in any of these other terms. It only shows up in this one term here. So we can kind of analyze the stability of the whole system just by changing this one term in this matrix. And again, this saltation matrix thing pops out, pretty ugly, but describes all 3 of those examples. And now we can apply the same idea of what we call hybrid event shaping. We can kind of change what's happening around the time of impact to improve our stability. We can apply that to any hybrid system. So as an example, here we're doing this 5-link biped walker. So it has motors at the hip and knee. The knee also has a hard stop so that there's an impact at the hard stop and there's an impact with the ground. And in this example, we're actually doing no continuous time feedback. So we're not doing any kind of LQR, learning, nothing. We're only controlling this by changing the shape of these hybrid events around a nominal open loop trajectory. And so if you just do a trajectory optimization to find a limit cycle, so find a stable or a walking gate where you end up where you started, and you try and minimize the total energy, so the minimum energy trajectory, after like 3 steps, you kind of blow up. If you have any amount of uncertainty in your state, that'll grow pretty quickly and you'll fall over. Again, we're doing no continuous time feedback. There's no sensing. So it's not too surprising that this unsensed humanoid is going to fall over. But if we do this hybrid event shaping, and we have 2 versions here, but again, it's things like that swing leg retraction, Rabert heuristic kind of stuff, but generalized to this sort of arbitrary system, we can get stable walking sort of indefinitely with no continuous time feedback. Now, I think you should also do continuous time feedback. I'm not saying we shouldn't have feedback control. But now our feedback control doesn't have to do nearly as much work. And so one of the things moving forward, we've now combined this in an ILQR framework So we're doing both ILQR to get an LQR controller, a continuous time feedback controller, as well as considering these kind of stability properties around our impact and actually throughout the rest of the trajectory. And so here for this sort of four-legged hopping example, if we don't do this and we just do regular ILQR, it kind of diverges after one hop. But here we're able to shape those impacts and get a stable hopping behavior. So again, the key idea here in this section was that by looking at these saltation matrices again, we can look at stability properties just analyzing them at the moment of impact, which is kind of cool. One place that we're trying to apply this sort of stability analysis is doing things like walking on narrow beams. So, I mean, the quadrupeds are pretty stable, so we got to kind of challenge them. So we're going to make it walk on a really narrow beam. And we're looking at sort of different walking behaviors. And one of the interesting that popped out of this was that the gait pattern, so whether it's a walking one leg at a time or a trotting, a two legs at a time motion, we thought that that would be pretty predictive of the stability. That actually doesn't seem to matter too much. The only thing that really matters is the duty factor, so the percent of time each leg is on the ground. And the sort of phasing between the legs was less important for stability. But in any case, this is sort of using that same analysis. So I've done a bunch of stuff talking about these hybrid system models of contact for state estimation, control, stability analysis. And again, this works great if when you watch the video of your robot, you can say, oh, here's where we're touching, and here's where we're not touching. So let's move on to these messier, more challenging things, where these hybrid systems, everything I just said, doesn't really apply anymore. So what happens in these cases? And let's really think about what was this hybrid model? What were the assumptions that went into that? So the four main assumptions that are baked into this, first was plastic impact. And I think plastic impact is almost always what we want in robotics. So in that paddle juggling, we needed elastic impact. But for the most part, with my robot, if I go touch something, I want to keep touching it. I don't want to bounce off of it, right? And so actually, I've done some stuff where plastic impact wasn't enough, and I made something that was more plastic than plastic impact. But in any case, plastic impact was one assumption. We assumed that there were no adhesive forces, right? So the ground pushes up on a robot, but doesn't pull us into the ground. The contact is rigid, so it enforces like a velocity constraint or an acceleration constraint between, say, your foot and the ground or your hand and the object. And finally, the contact doesn't change the surface, doesn't change the thing you're touching. And so the state, if we want to describe the system, we just need to know where, in this case, the height of the ball is. There's no state in the ground. We don't need to know the height of the ground. That's constant. So of these, I would say the top two are pretty easy. We can relax these, and this kind of hybrid system framework still works pretty well. And the bottom two are a little harder. So let me go through a few quick examples, and we'll look at all of these. So the first was, let's look at adhesive forces. So this is a magnetic wall climbing robot. And so now we stick to the wall, right? We get a force into the wall. And this still fits into this kind of hybrid system framework. So, nominally we would say, oh, our normal force has to be positive. Now it's just sort of offset. Now it needs to be greater than some magnetic adhesion force. But otherwise, structurally, everything works out the same. And this was a neat design that was very good at doing these kind of floor to wall, wall to ceiling transitions. And there in the middle, the yellow thing in the middle is called a PXRF, portable X-ray fluorescence sensor. So we can kind of make these transitions and then scan for contaminants on the surface as we're going. All right, so adhesive forces. There's another kind of adhesive force we've used from microspines. So a lot of this comes out of Mark's lab originally. And for microspines, there are these little fish hooks that grab onto little bumps on the rocks. And here you see there's sort of these 10 red fingers. Each one is individually compliant and has its own little fish hook. So the individual compliance is important because they have to maybe stretch to different lengths so that each of them can grab onto its own little bump. But then if you do that, you get enough of them to hook on, and you can kind of grab onto the rock and climb up. Here, the microspine, instead of our normal force being greater than 0, we have this other kind of formula that approximates what forces are allowed. It kind of looks like a friction cone, but it's a little different. But again, it still fits well within this framework of hybrid systems. We just have a slightly different contact model at the base of it. So with these microspines, we can make climbing robots. So this was our Loris robot that we presented at ICRA this year. They can do cinder block or slag or other kinds of rocks. This was my only student who was excited to be in a cinder block office. This was his office, actually, where he filmed this. We've gotten them out of that ugly office before. And then this one's funny. We were trying to get a bunch of rocks to build a wall in the lab, and we're in Pittsburgh. And slag is this byproduct of steelmaking. They normally have to pay to get rid of it and store it somewhere. And so if you show up with a truck and say, hey, can we have some slag? They were like, yes, by all means. So we got a free slag wall out of that, which was good. And it turns out to be great for climbing on. All right, so those are sort of the easy things to change. Let's get into the things that really break these hybrid system assumptions. And so the first will be vegetation. So we looked at this earlier. Let's say we're walking through and we're getting hooked on these vines. All right, as I'm watching this video, I don't know when it's touching what, right? We can't kind of tell, oh, we're touching this vine at this time and that vine at that time. And even if we could, I don't know the model of those vines. I don't know their stiffness. I don't know how extensible they are. And I don't want to, but I don't want to try and model that. So how are we going to make progress in this where we have contact with the world with large amount of uncertainty, both in the model and in the state that we have here? And so our approach, there's sort of two parts to it. The first is we use what's called a link momentum observer to tell when we've hit something. And so this is taking, we know how much torque we apply to the leg. We know the dynamics of the leg when it's not touching something. So we kind of know what the momentum should be nominally. And then if it's not that, there must be some external force. And if that force is higher than some threshold, we'll say that we've hit something. But we haven't figured out where we're hitting or what we're hitting. So then the second half is we need a reactive controller. And here in this simulation, we're showing each of these pluses as a vine that it could get caught on. And we're going to come up with a control strategy where whatever is touching us, anywhere on our leg, we'll come up with a strategy to kind of push that to the edge of the leg and get over. So now we don't need to localize that contact. And we come up with a way to get through it wherever it is. And we also don't need to have a perfect model of the forces or the stiffness or any of that kind of stuff. And so this works well on a variety of things. So here we're showing a low stiffness. This is a bungee cord. There is a stiff rope. Here this is a rigid beam, like a metal plate. And then this one is some kind of robot torture device that has all of those things put together in sequence. And so again, here it's just sensing, hey, my leg's not moving the way I thought it should. So let me do this reactive behavior and get over it. Yeah.
So can you apply this method to the earlier hybrid model scenario? Will it just work for those as well?
Yeah. You can definitely do this kind of stuff for rigid plastic impact kind of contact as well, certainly. And we have done that. And there you can get even more. So we've done stuff where you can actually localize where on your leg you're touching if you assume that the thing you're touching isn't moving. If the thing you're touching is also moving, then it's really hard to sort of figure out both where and what you're touching. Yeah. We took it back outdoors, although it's Pittsburgh and we have seasons. So this is actually the same ivy patch, but in winter. So it worked outdoors as well. And I'll quickly mention all of the quadruped stuff that we do in my lab is available as part of this Quad SDK. So this is our open source quadruped control stack. So it does high level planning, like jump over the gap or go around the obstacle. The middle level model predictive control that says what forces do I need to achieve that trajectory. And then the low level controller, state estimation kind of stuff. And I would say this is a pretty standard, the baseline here is a pretty standard quadruped control framework. And then most of the research in my lab is improving this, or trying to beat it here, or comparing this. And so I encourage you to download it and then do better than it with whatever you're working on. All right, so then let's talk about sand. So now we have something where, all right, we're touching kind of continuously over the whole surface. And what's worse, the thing we're touching is moving and piling up and sifting around us. So this is a test on the one of the Viper test rigs. In this case, we told this motor to pretend that it was broken and stuck. All right, so if we send this to the moon and one of the motors dies, how can we continue to make progress? Can we survive that kind of failure? And what do we want to do with the other wheels to kind of compensate for that? So to look at this, we built up a Terra mechanics model looking at kind of stress and friction along the surface, both of the wheel as well as the side of the wheel. We ran a bunch of wheels through sandboxes to collect a bunch of data. And long story short, our model, which is the line, kind of lines up with the dots, which are the experiments over here. So with this, we can make predictions about wheels that are doing things that are very different than standard driving. So this is now compared to previous models, we can handle a wide range of angles. So we have the wheel stuck at some weird angle, as well as slip ratios. So you can have one wheel spinning backwards and the other three spinning forward, and still get pretty good force predictions. And it's a pretty quick model to evaluate, so we don't have to simulate a million grains of sand to figure out what the forces are. And so with this is our sort of mock rover. Again, this back right wheel is damaged. And so here, if we do nothing, we kind of veer off to the right and don't make it to the end. And now with this sort of force model, we can come up with a feed forward or a feedback controller that keeps us on track, changing what the other wheels are doing. We can also use this to intentionally do weird things with our wheels. So here we're trying to dig a trench in the sand by taking this back right wheel, turning it at an angle, spinning it faster. And in this case in particular, we wanted to get a trench where all of the sand we were displacing was piled up on one side, and we had a clean face on the other. So wherever the sand is piling up is going to fall back in. But on the right side, in that case, we can kind of clearly see the strata of what the soil looked like undisturbed. So we have this kind of trench-shaped model that we can make and predict, based on your driving conditions, what kind of shape, how deep, how wide, what does the pile-up look like for that. So some concluding thoughts. Overall, in my lab, we think a lot about the two key challenges of contact. How are we touching the world, and in particular, the discontinuous nature of contact, as well as uncertainty, and trying to come up with methods that handle large uncertainty. Briefly, I got time. A couple other fun projects that are going on in the lab. One is that I have a paleontologist in my lab. So if robots aren't cool enough, we now do dinosaurs and robots. And she came to us because she was asking questions like, how did these little dinosaurs get over big obstacles? And what was the first animal to run instead of walk? These are really sort of dynamics and behavior questions. And her challenge is she can't observe the animals that she's interested in. And so she's interested in how robots can help paleontology to build physical models or simulation models. But we can also go the other direction and think about what can paleontology do to help robotics. So if you believe in bio-inspired robotics, 99% of all species, more than, are extinct. Most of the diversity in living things is extinct. And so if we're only looking at the living animals, we're missing out on a lot. And so just because a dinosaur wasn't robust to, say, earthquake or asteroid impacts, right? It was otherwise a pretty good design for a few, like 100 million years or something. There might still be some good insight to have from that. So can we look at things like convergence of design when features re-evolve, or look at the first occurrence, like the first animals to walk on land, the first animals to walk in a new environment. What had to change to enable that? One of the things in particular we're looking at is spines. So animals generally have spines, and we seem to be doing lots of cool things with them. Robots almost never have spines. They're all bricks with wheels or legs attached. So what are we missing out on in terms of spines? Another project that sort of deals a lot with the uncertainty side, today was mostly more about contact, is sort of learning how to drive over rough terrain. And here, maybe I can have a model of the robot, but honestly, these are really squishy tires. It's got a complicated suspension. We don't really have a good model of these. But we certainly don't have a good model of that pile of gravel or the grass or that kind of stuff. So we'd like to use machine learning, but we don't have a good model. So that means we can't train in simulation, and collecting data in the real world is slow and expensive. So how do we use a lot of simulation data that's wrong, but it's close, like it's roughly right, within a little bit of real world data? And the key idea here in simulation in the upper left, these different colored robots all have slightly different dynamics. And rather than doing the sort of standard sim to real thing of just randomizing all of that and throwing it into one policy, we keep them all separate, and we train both a dynamics model as well as a system identification transformer. And so we're sort of learning both the space of possible dynamics, but also how to figure out where in that space your particular system is. And then online, you need just a little bit of data to figure out where your actual system lies in that sort of dynamic space. So that's the key idea there. That was at ICRA this year as well. Before I wrap up, two quick things. One, faculty positions open at CMU. So if you're interested in that, come talk to me afterwards. Happy to answer questions. I'm not on the search committee, but I can maybe give you some insights. One thing to know about Carnegie Mellon is that we have something called the Robotics Institute. It is a department, and it is under the School of Computer Science. There's also people like me that are in mechanical engineering, where you might think robotics lives. And the short answer is you should probably just apply to both. And that's true also if there's any master's or undergrads looking for PhD programs, you should probably apply to both, or at least look at both as well. And so there's, for faculty, there's both MECI and a robotics search going on this year. And then the last thing I wanted to talk about was supporting diversity in robotics. And so hopefully it's not a surprise to anyone here that the diversity of the robotics field looks nothing like the diversity of the rest of the country or the rest of the world. And what's more concerning is that these trend lines aren't really changing very quickly. So there was a study that looked at women in robotics, and it predicted that at our current rate, we'd reach gender parity in like 2055 or something. It's going really slowly. And so it's very clear to me that nothing's going to change unless we take some concerted effort, some actual actions. So I encourage everyone here individually, or as a research group, or as a university, think about what you can do to help support diversity in robotics. I have some suggestions here. The first is to join a networking or advocacy organization. So there's Black in robotics, women in robotics, queer in robotics. You can go sort of broader. There's Black in engineering, Black in computing. I'll point out your own Monroe Kennedy was one of the founders of Black in robotics. And I've been working with them as well on a bunch of projects. I encourage you to read, cite, invite, mentor, collaborate with a diverse set of researchers. And so if you're not sure who those researchers are in your area, you can go to the Black in Robotics reading list that we maintain. And there's also this U.S. Women in Robotics that have sort of topical areas. And you can go find cool research in your area from a diverse set of researchers. And finally, I encourage you to spend some time to learn more. So we have this supporting Black scholars in robotics. This was an IEEE Spectrum article. And then there's these great action item lists from Black in engineering and Black in computing that have a lot of good suggestions there. So with that, I'll wrap it up and take any questions. Yeah.
I have a question about the example you gave about navigating the vegetation or other complex environments.
Yeah.
And also just related to that with the bio-inspired robotics. I was wondering if there is any like experiments testing whether the robots just walk on like two legs, just like stand up and all like four legs, because when you have like four legs or more legs, it's more contacts.
Yeah, so there's more legs to get caught on vegetation, certainly. I would say the flip side is usually bipeds are less stable than quadrupeds. And so actually if you're, brushing up against a bush or getting caught on vines, you'd like to have as many contact points as possible. All right, so it's much harder to knock the quadruped over than a humanoid, right? So yeah, now you're right. There's more things to get caught, but I think on average, the quadruped is going to be much more stable and more successful there.
Like for example, this the spot, like it just like stands like upside down, and then the back legs sometimes.
Yeah, there's been a couple bipeds that kind of have the same two-leg, looks like two quadruped legs only. I think mostly you can do it. It's without an ankle, you're sort of pretty unstable, and so you have to kind of constantly be walking around like this because you're up on your tippy toes. And so like you can do it briefly, but you'll probably fall over pretty quickly. Yep. Yeah.
Thank you for the great talk as always. I have a question regarding solidation metrics.
Yeah.
Do you theoretically ever encounter zero kind of behaviors there, and the solidation metrics take care of that?
Yeah. So Zeno is tricky. So Zeno is when you have an infinite number of transitions in finite time. So if you picture a bouncing ball, it gets smaller and smaller and smaller and smaller, and it still takes an infinite number of bounces to get to zero. There is a problem at the end there, because one of the conditions we need for a saltation matrix is this transversality condition, where you need to have neighboring trajectories all impact the same guard. And then when you're getting close to zero, some neighboring trajectories are below zero and some are above. And so you kind of won't have this transversality. But if you do like there's methods that do continuation methods where you kind of, if you detect that you're in this and you do something to kind of try and jump to the end, you could do the same kind of sensitivity analysis for that jump to the end process. Yeah.
Does operating in discrete time helps us in any way, because by operating in discrete time, we're getting infinite jumps.
So discrete time dynamics, it's kind of, you're always discontinuous in some ways, right? You're always jumping by some discrete amount. But I would say, if it's small DTs, then, usually your velocity changes a little bit until you impact something, and then it changes a lot in one time. And there, again, if that transition happens one DT early or one DT late, that's going to have a big influence on neighboring trajectories. So I mean, kind of technically it doesn't quite apply there, but if it's approximating smooth dynamics, you'll get approximately the same problems.
Yeah. Is there any materials that can do like state transition very fast and control, and also real time, such that, for example, if those materials are used for sensors or tires that goes into contact with actual surface and changes?
So there's certainly a lot of contact sensors that can operate. Some operate faster than others. I talked a lot about contact. I didn't really say much about sensing contact here. It's because a lot of sort of contact sensors like switches or tactile sensors, they're either not robust, so they don't survive well if you smack them against the ground a couple times a second, or they're sort of slow and have a lot of hysteresis and stuff. There's certainly some sensors that would be much faster. And in terms of state estimation, the more accurately you can predict whether you're in the air or touching the ground, those are very different dynamics. And so the better you can estimate what your contact state is, the more successful your control or planning or learning will be. Yeah. Yeah.
The screen itself of the vines, it doesn't know how high it needs to go to get out. So it's just waiting until it doesn't feel the tug anymore.
Yeah, so it's actually coming up with a trajectory where if there was a vine anywhere along the length, it'll get it to sort of slide off the end. And the way you can kind of sort of picture this is, as we're moving forward, we know it's touching on this surface, right? If there's a vine behind us, that's fine. It's not going to slow us down. So we move back a little bit, and then we pull it forward, and then we push forward with the back of our leg, and then we can extend the leg down. And so then wherever it's touching, we'll get over and push the next vine down and continue making progress. Yeah. So.
Is that something that the designers came up with? That strategy.
I think it's actually implemented as something the designers sort of have tuned, but you can try and solve for that as a trajectory optimization as well. Yeah. Yep.
Going back to so traversing through sand, I wasn't super clear on what the difference was between feed forward and feedback for the adaptation to.
Oh yeah, they look pretty much the same. I mean, the feed forward, if you go and bump it, won't know that you bumped it, right? And then the feedback will correct for that. So the feed forward over a long distance will kind of drift, and the feedback will sort of stay on there. And it's all using that force model. So we need a way to predict the forces of how we're interacting with this sand. And I don't think I mentioned it, but that force model also we use a model of where the sand is flowing to tell where it's touching our wheel. But in any case, once we have that, then we can do. We did like a force balancing optimization to come up with the driving angle and speeds for all of the wheels for the nominal trajectory, as well as a sensitivity to say what's the best. Like if I'm turning a little bit to the right, what's the best correction to steer back onto track? And so then that's what the feedback policy is using. Yeah.
Is it possible to, put sensors on like a live animal so that and the sensors are positioned like identical to how the robot would sense the different metrics in the environment and just like monitor how if the robot was functioning like a live animal, like a dog or cat, like what
you certainly could, and we do this mostly, I would say, with humans, right? We put sensors in shoes, and we look at pressure distribution and center of pressure kind of properties, and people try and use that for control targets. You have to be a little careful because I would say anytime you put a sensor between you and the environment, you're changing that interaction. Now, we do that intentionally with shoes to make that a better interaction. But with animals, you often have trouble where if you put a little booty, like on, I don't know, like if you've ever watched these things with cats, if you put something on their feet and then they like get really freaked out because doesn't feel the way that it usually does. So anytime you add a sensor in between, you're changing the mechanics of that interaction. And sometimes that can cause problems with animals, especially. Yeah. Yeah.
Can you speak a bit more about the intuition of swing leg retraction? Why do humans do it?
Yeah, the intuition. Yeah. So sort of like the zeroth order of like, you want your leg to roughly be zero velocity, so you don't scuff. And then coming backwards means that if you touch down late, you'll be pushing backwards a little bit more, and that's going to push you forwards, right? If you touch down early, your leg is moving slower. You can also think of it as it's both the velocity, but then it's also changing the angle that you touch down. So if you touch down late, meaning you're too slow, you'll be at a more vertical angle. And if you touch down early, you'll be at a more shallow angle, and that slows you down. Yeah. Yeah, and so, I mean, there are very easy mechanical explanations for these. And so that's how people have figured out these kind of heuristic controllers, for decades. It started by observing humans, and we saw that humans do this. I would say on that little biped robot, it's just applying sinusoidal output to that motor, right? We're not programming in swing leg retraction. we're programming an oscillatory motion. The stable gait that comes out of it has this swing leg retraction because that's the stable gait, right? And so it's sort of the phasing of the contact lines up so that the leg is coming back when it impacts, because that's the stable walking gait.
We should probably wrap up.
Yeah.
All right. Thank you once again.